Hello everyone, my name is Carmelo Cascone. I'm an engineer at the Open Networking Foundation. It seems these days every organization is a P4 guy. I'm like the P4 guy. I mean, I think I'm not the only one right now, which is good, meaning that there's more interest in P4. I have like other people helping me out, which is good. So in this talk, I'm gonna talk about the way we added support for P4 and P4 runtime, which is not just like a new technology, actually like a completely different way of handling the data plane. And I also provide two examples of how these decisions we made and the design we applied was proven to be useful. Okay, so before I start, let me clarify a bit terminology. We're going to talk a lot about pipelines here. What is a pipeline? There are different pipelines in this word. The kind of pipelines we're talking about are those you find on a switch or a network interface card or almost any other high-performance forwarding device. So in these devices, you have a chip. This chip can be an ASIC, can be an FPGA, or a CPU in case you are using a software switch. What happens that most of the times, if not all the times, the internal architecture of the ASIC or the way you program your FPGA or the way you implement your packet processing logic in the CPU takes the abstraction of a pipeline of tables, match action tables, the same tables that became popular with OpenFlow. I mean, match action tables have been there like for so long, but I guess OpenFlow brought it to the masses. So we have pipeline, and today we have P4, which is nothing else than a programming language to define these pipelines. A lot of people are questions like, can I do this with P4? Can I do something else with P4? And usually the answer is, yeah, P4 is a programming language. Most of the times it allows you to specify these ideas you have, but then when it comes to actually implementing this or that function on a device at high speed, terabits per second, then it really depends on your compiler target for P4. So yes, P4 is a programming language. Or maybe better, domain-specific language can be used to describe things like protocol headers, the parsing logic to extract those headers, the lookup tables, so the match action tables, the actions to apply to the packets, counters. It's good enough to describe both high-performance targets like a switching ASIC or an FPGA, as well as lower ones like a virtual switch. It's good not only for programmable switches, but as we found out at ONF, it's also very good for fixed function devices, as it serves the purpose of defining a contract for a runtime operation between the control plane and data plane on the actual capabilities of the data plane. I need to do bridging. I need to do routing. Like which tables, can I use to insert a table entry that does longest prefix match on the IPv4 address? You will find this information on a P4 program versus, before P4, you had to read the manual and find out, which tables can actually support that function. This is the workflow you usually find with P4. You have a P4 program, you have a compiler, usually provided by a switch vendor. This compiler, in the case of programmable ASIC or forwarding device, it's used to actually compile the P4 program and realize this given pipeline on the device. In the case of a fixed function ASIC, what the compiler produces, or a human compiler can produce, is actually a mapping between the logical tables defined in a P4 pipeline and the physical ASIC tables. So once we have a P4 program, there you have an example of a little P4 program for a very simple routing table. Then it comes runtime, because P4 can be used to define the tables, but then to forward packets, we need to populate these tables. In the case of a router, maybe we have a switch local control plane implementing, OSPF, BGP, and this will be responsible for populating those tables. So this is what we mean with runtime control when it comes to P4. It means nothing else than populating tables that were previously defined using P4. The de facto standard for runtime control of P4 defined match action tables is P4 runtime. You might be asking yourself, can I just use OpenFlow or any other mechanism? Yes, you could use OpenFlow. Indeed, OpenFlow in a way is a protocol to manage tables, to write and read table entries. The problem is that OpenFlow has some limitations when it comes to P4, and the limitations stand in the fact that OpenFlow is restricted to a subset of protocol headers and actions, Ethernet, IPv4, IPv6, and very specific actions that allow you to operate only on those protocols. P4 allows you to do much more. P4 allows you to define processing for new custom protocols, so you'll be restricted by using OpenFlow. Indeed, the main difference between P4 Runtime and OpenFlow, and also other APIs, is that P4 Runtime is a very simple, super generic API to do table management. Table management and something else, like packet I/O, sending packet outs, receiving packet in. But at the end of the day, it's a very simple API that is completely data plane protocol agnostic, meaning that there is no knowledge of Ethernet address, IPv4 address. Use P4 to define the pipeline. Use P4 Runtime to populate those table entries defined with P4. It's the result of a community work from the P4.org API working group. It's based on initial contribution by Barefoot and Google. You can find the release candidate of the first version of the specification at that link. It's based on gRPC and protobuf, which are great things because not just performances of the RPC, but also because we can easily generate the client and server code to implement control plane or a switch agent. As I said, it's independent of the P4 program and the protocol supported by the P4 program, and that's because the API itself allows a control plane to push a runtime completely new pipeline and change the capabilities of the device without actually recompiling the switch software stack, which is something you have to do if you use OpenFlow. If you use OpenFlow and you want to add a support for a new protocol, you can do that. You can modify the protocol, but then you probably have to recompile the switch software stack. This is the workflow you get with P4 and P4 Runtime. You have a compiler, you have a P4 program. You compile that P4 program and you get two outputs. The first one are the target specific binaries. This could be, for example, the bit stream to program an FPGA, or the configuration for a programmable ASIC, or the mapping for a fixed function one. The other, sorry, I thought there was a laser pointer. The other output of the compiler is what we call the P4 info file, which is we can define it as a schema of the pipeline. It's what you will see if you look at the pipeline from the top in terms of which tables are available, which match fields can be matched on each table, which actions are tables. And the P4 info basically contains all the information needed by the control plane to operate on that pipeline. And that's why we say that the P4 info is what defines the contract between the control plane and the data plane. And that's what it's used by the control plane to actually populate, to actually format the P4 Runtime messages to, for example, populate tables. It's based on protobuf, meaning that we can easily serialize, deserialize P4 info in a control plane. It's target independent, meaning that you will have the same P4 info if you're controlling an FPGA-based device or a ASIC-based device. Okay, this was the introduction. Now let's move on to ONOS, and I'll describe with some slides how we added support for this new dimension of programmability in ONOS. So these were the design goals we set when we started working on this. I think it was last year, around May timeframe. So we said we want to allow every ONOS users to be able to bring their own P4 programs. We don't want to restrict the system to a subset of predefined pipelines that maybe are convenient for ONOS for its operation, but we want to really open up this possibility to all ONOS users. While doing this, we want to make sure to allow existing applications to be able to control any P4 defined pipeline without changing the application itself. And this is very important if you take the example of Trellis. Trellis is a very prominent set of applications. It's designed to run at production, a lot of work behind it. Clearly, if you want that support for new silicon, new P4 capable silicon, you want to make sure to keep using the same application. The second goal is that to allow, at the same time, applications to be able to control custom and new capabilities that are enabled by P4. With P4, you can support processing of unusual protocols, like you will never imagine to process on a switch. Let's say GDP tunnel termination or other kind of functions. Well, we want to make sure to enable ONOS to enable ONOS application to control these new capabilities defined in P4. Before I move on, the next slides are going to be a little bit more technical. I don't know how many of you have development experience with ONOS, but I guess the message we can abstract from the next slides is that I think when ONOS was conceived, the initial design decisions that were put behind ONOS were fundamental to enabling this, because we were able to add support for this completely new level of programmability and flexibility without reinventing the system. So thanks Thomas, Ray, like all the ONOS developers who were there before, this work was pretty easy. Okay, so the first element in the P4 enabled ONOS architecture is what we call a Pipeconf. A Pipeconf stands for pipeline configuration, and it's basically a way to bring your own pipeline. Pipeconf is a way to package together all the information needed by ONOS to understand, control, and deploy a given pipeline to a device. It can be distributed as an ONOS application. It's indeed an ONOS application. It simply informs ONOS that a new pipeline is available to be deployed to a device. And it contains mainly three things. It contains the pipeline model, which is a description of the pipeline capabilities that is understood by ONOS. And this is automatically derived from the P4 info file that it's generated by the P4 compiler. It contains some target-specific binaries to deploy the pipeline to the device, meaning that if we're trying to program an FPGA-based device, we will have the FPGA bit stream inside the Pipeconf. If we're trying to control Tofino-based switch, we will have the Tofino configuration files inside the Pipeconf. It also contains some pipeline-specific driver behaviors. If you're familiar with the ONOS architecture, ONOS has this very nice layer of abstraction, the driver layer that allows anyone to provide a different implementation of a given capability for a specific device. In this case, some of the let's say operations might depend on the pipeline, and so we are able to provide an implementation of those driver behaviors as part of the Pipeconf. An example of this behavior is the pipeliner, which is used to map what we call flow objectives to a specific table entry of a P4 defined pipeline. The flow objective, if you're not familiar with it, it's a northbound API in ONOS that allows applications to program to control the network in a pipeline independent way. I'll talk more about this later. This is kind of like a high-level picture of what the architecture looks like, the Pipeconf-based architecture looks like. Once you have your Pipeconf, you can register this Pipeconf to a Pipeconf store or Pipeconf service. And then on top, you have two types of applications. You can have pipeline-agnostic applications, and you can have pipeline-aware applications. Pipeline-agnostic applications are those applications using pipeline-agnostic APIs, like the flow objective. And an example of this application is Trellis. Trellis was designed initially to work with Broadcom-based silicon and OF-DPA, but likely the people that were working on Trellis decided to use a pipeline level abstraction to do that, and this is the flow objective API. On the other side, we have pipeline-aware applications, and these instead are applications that program specific tables and specific capabilities of the pipeline. And this application can only work with devices that expose that specific pipeline. Then in the core, we have things like the PI framework that I will talk about later, and translation services. These translation services are used to, for example, map between flow objectives and the table entries of the specific pipeline. We have the driver layer. We have protocol generic drivers like P4 Runtime, and I also put there GNMI because it seems to be very related to P4 Runtime these days, if you heard all the talks about Stratum. We have a Stratum driver that combines the two things together, GNMI and P4 Runtime, and then we have device-specific drivers like BMV2 that extend the P4 Runtime driver. BMV2 is a P4 reference software switch. We have barefoot drivers to control Tofino-based devices, and also we have experimental support for Mellanox Spectrum 1-based devices. When it comes to pipeline-aware application, the way we support new capabilities and like new protocols, things like that, is we were able to, with a very minimal extension to existing flow rule API, allow application to simply specify generic match action relationship using just the name of the header fields and the actions as specified in the P4 program. What is this PI framework? The PI framework is a set of a number of classes in the ONOS core API. PI stands for protocol independent. In this case, we mean data plane protocol independent. So there is no mention to IP, Ethernet, MPLS, things we can match and actions we can perform. We have three categories, three different type of PI classes. We have model classes, runtime classes, and service classes. Model classes are used to represent the pipeline model, and these are honestly derived from the P4Info abstraction. It's basically a Java representation of the P4Info. We have runtime classes that are derived from P4 runtime. So we use runtime classes to, for example, define a table entry, the same in a similar way you will do with P4 runtime. And then we have service classes that are used to operate on P4 capable devices. So how do you discover and deploy the given P4 program to a device? So the red blocks are ONOS core components, the green ones are device drivers, and the blue ones are Pipeconf elements. So the first thing you need to do is register the Pipeconf to the system. In this case, we are registering a Pipeconf called myPipeconf that provides two extensions, the P4Info that it's always required to generate a pipeline model, and some extensions. In this case, we are providing as an extension the BMV2 JSON, meaning that we can use this Pipeconf to program the BMV2 software switch, but you could provide also extensions for other targets, say Tofino, FPGA, something else. Second, you push to ONOS a JSON file, the network configuration file, in which you provide the, for a given device, you provide the IP address and port of the P4 runtime server, the ID of the Pipeconf you want to be applied to the device, and the driver. In this case, this is a BMV2 device, so we're using the BMV2 driver. After you do this, ONOS will take care of opening a gRPC connection to the device, and then we have a Pipeconf service that will deploy the Pipeconf. We also have this operation called driver merge, Pipeconf driver merge, that is performed by the driver manager, and I will explain what it is now. So as I said before, in ONOS we have this very nice layer, the driver layer. So the way we were able to add, to basically have ONOS be independent of the pipeline-specific capabilities is simply by reusing the driver subsystem. So the idea when you use a P4 programmable device in ONOS is that you have to select a device driver and a Pipeconf. The Pipeconf brings in some driver behaviors, and what ONOS will do will merge these two drivers. In this case, we have a BMV2 driver. In the other case, we have a Pipeconf that provides a collection of behaviors, and then the system can use this merged driver. This is an example where the existing ONOS architecture worked very well to provide this new level of flexibility. Example of Pipeconf behaviors that I have there are the pipeline interpreter and pipeliner, and I have an example of how they work in the next slides. We also have what we call translation services, and translation services are there only for one purpose, is that, I mean, even if we did our best to make ONOS control protocol independent, clearly when ONOS was designed, OpenFlow was the main SDN API, so ONOS is strongly inspired and influenced by OpenFlow. That's why the flow rule abstraction in ONOS, even if doesn't have the OpenFlow name in there, it really looks like an OpenFlow flow rule. So you have matching capabilities on specific standard headers, and also you have the action API really looks like OpenFlow, in which for a given flow rule you can specify a list of actions, which really doesn't work well with P4. In P4, instead, it's more closer to the hardware, where for a given match you can only execute one action. That action can have multiple parameters, but there's no such a thing as combining different instructions or primitives at runtime. So we have translation services that serve the purpose of translating what we call protocol-dependent ONOS entities to protocol-independent ones, but they also serve another very cool purpose, which is they provide validation, right? We don't have to wait to send a flow rule to the device or a group to the device to learn that that specific device doesn't support routing on table 30. Okay, or doesn't support bridging on some other table, or doesn't support longest prefix matching on a given field. The validation is provided directly by the translation services, and that's because at the control plane we have all the information we need to make sure those entities can be installed to a device, which are derived from the P4 info file. This is an example of how we perform flow operations. So we have what we call a three-phase translation. So assuming we have an application that is pipeline agnostic, so this application is programming the network using flow objectives. In the first translation is where we translate one flow objective into many flow rules. In this case, the flow rules are specific to the given tables of the pipeline. And this is operated by the pipeline or driver behavior, which is provided as part of the Pipeconf. Second, we translate each flow rule to a table entry. In this case, what we do, we simply map from standard, for example, header IDs like Ethernet destination address to the actual name of the Ethernet destination address in the P4 program. We do the same thing for actions. And finally, in the last step, in the protocol level, we do a mapping between the stable entries to P4 runtime protobuf messages. In the case of pipeline-aware applications, you will be skipping the flow objective layer. So in this case, the application will be emitting directly flow rules. So this will go, in this case, we have a two-phase translation. So this is a summary of all the P4 runtime features supported in ONOS today. We don't have a complete support for all the P4 runtime capability. We have support for probably the most important things like managing table entries, supporting packet ins, packet outs, managing groups that in the P4 runtime world are called action profile groups or multicast groups. We can manage meters, read counters, and clearly we can deploy a given pipeline configurations. There are many features that we don't support, like parser value sets, registers, clone sessions, and like if you like to contribute to ONOS and you don't know where to start, like this could be a good start. So feel free to get in touch. Okay, now that I've described at very high level how we support P4 and P4 runtime in ONOS, I'll move on to some use cases. But before I do that, how much time do I have?
You got 10 minutes.
Okay, that's good. So the first use case is Trellis. Like I think we're Trellis a lot of times during these 3 days, which is great because Trellis is simply great. Trellis was initially designed to work with Broadcom silicon, white box switches running OF-DPA, where if you're not familiar with it, OF-DPA, it's an OpenFlow agent exposing a logical OpenFlow pipeline that works across many different Broadcom silicons like Humern, Tomahawk, Trident 2. In this case, Trellis is nothing else than a set of applications running on top of ONOS, where these applications are pipeline agnostic, meaning that they use the Flow Objective API. So the way we added support for P4, it's very simple. We wrote a P4 program called fabric.p4. We created a Pipeconf around it. This Pipeconf provides some drivers to the system that are able to translate the same flow objectives provided by the applications to the specific tables of the pipeline. So we added support for Trellis without changing the Trellis applications. So by simply working at the driver layer. So what is fabric.p4? Fabric.p4 is a P4 implementation of the Trellis underlay reference pipeline. That's because in Trellis we have underlay and overlay. In this case, we only work at the underlay. It is inspired by Broadcom OF-DPA. I think Broadcom did a great job in trying to abstract commonality between different SDKs and different physical pipelines. This is open source, so we took inspiration from it. But it's a much simpler pipeline. It's tailored to Trellis needs. I think I've heard many times during these 3 days this thing where P4, yes, it's great to add new capabilities, but it's super great to actually remove things you don't need. So remove tables you don't need, things that yes, you can do that to optimize resources, memory, or just because like seeing those tables in the pipeline just confuses you when you're trying to control that pipeline. So it's really it's much simpler than OF-DPA. It's a work in progress. We may support for some features, like for example IPv6. It's important to say that this works with both programmable and fixed function chips, and that's because Fabric.P4 it's a logical abstraction of standard features like layer 2, layer 3, MPLS routing. We're not doing anything new, so any switch pipeline that can be mapped to Fabric.P4 can be used in Trellis. And clearly, any switch that exposes a P4 runtime server, so any Stratum-enabled switch, can be used in this case. It's open source. Fabric.P4 comes with ONOS, and we say it's extensible because it can be extended with some other features, as I'll explain later. This is an example of what the Pipeconf looks like in the ONOS code base. So we have the implementation of the Java implementation of the pipeliner and other driver behaviors. It comes with some P4 compiler outputs, in this case for the BMV2 software switch. In the future, we hope to instrument the ONOS build to be able to actually generate the compiler output for a given P4 program, so we don't have to ship auto-generated files in the code base. The same Pipeconf can be used to support both software switches and actual hardware switches like Tofino, and we have experimental support for Mellanox Spectrum 1. Yes, the P4 code comes with ONOS, as I said. We also have this very nice make file that if you look at it, it shows this thing where you can use Fabric.P4 with multiple profiles. You can have the basic profiles in which you have the basic forwarding capability, but you can also compile Fabric.P4 with support, for example, for serving in packet gateway offloading or like high-NT in-band network telemetry. We say that Fabric.P4 enables what we call easier silicon independence. And I say easier because ONOS already provides silicon independence. We have this nice layer of abstraction, which is the flow objective, where the flow objective is kind of a pipeline abstraction, but it's standard specified, it's ambiguous, was created by like Java developers, and like Java is not a pipeline abstraction language. So it's hard to map flow objective to new devices. Indeed, we started with OF-DPA and Broadcom ASICs. We added support for some other ASICs using OpenFlow. I think it was Mix Client. And to do that, we had to implement this very complex driver that does this pipeliner mapping. With Fabric.P4, things are different because we define our logical pipeline abstraction, and we leave the duty of creating this mapping to P4 compilers or ASIC vendors. I say ASIC vendors in the case there's no such a P4 compiler, but you can still come out with a manual mapping of these logical tables to the physical ones. And that's easier not just for the ONOS developers because we have to do less work, but also for whoever is creating this mapping. And the reason is that because P4 is a formal language, you can use nice tools like, for example, data plane unit testing. So we created a unit testing suite for Fabric.P4. We use what is called this packet test framework that is similar to OF test, but without OpenFlow. So we have this nice project, which is, by the way, open source. You can find it under the ONLab GitHub account, that simply tries different forwarding behaviors on a given device. So after you program a device with Fabric.P4, it generates some inputs, in this case are packets. Actually, first programs the tables using P4 at a time, generates some inputs, packets, and verifies the output. Now, this is not the first time someone is coming up with the data plane unit testing suite, but the nice thing is that by using P4 and by using the reference software switch, first we are able ourselves to check the sanity of our P4 code, so we are able to validate our implementation, and then we can give this tool to ASIC vendors and make sure their compilers works well to pass all the test cases. Just to give you an idea of why Fabric.P4 also makes it easy to provide this full objective mapping layer. The design rationale behind Fabric.P4 actually comes from the flow objective abstraction. So in ONOS, we have this abstraction that is more or less an abstraction of a three-stage pipeline. We have a filtering stage, forwarding stage, next stage. And what we did, we simply created almost a similar abstraction when writing the P4 program. So we have some tables that represent the filtering stage, some other tables represent the forwarding stage, and other tables that represent the next stage. With this, the benefit of this is that if you look at the implementation of two pipeliners in ONOS, so we have the OF-DPA pipeliner and the Fabric P4 pipeliner, the OF-DPA pipeliner has 3 times more line of codes than the Fabric.P4 one. Because this is basically a one-to-one mapping between that flow objective abstraction and Fabric.P4. You might be asking, why do you need 2,000 lines of code for a one-to-one mapping? Well, you know, Java, like, you have to import, a lot of packages. It's verbose by nature. Another interesting feature, benefit of P4 when it comes to Trellis, is that we use Trellis in different use cases. We have NFV Fabric for access. We also have SIBA. In the first case, we prefer to have a small bridging table, but dedicate more memory to the routing part. In this case, 100 times more entries than bridging. Then we have SIBA that works in 2 different modes. We can have double VLAN cross connect or double VLAN termination. In the first case, it's no routing. It's mostly we dedicate most of the memory to the VLAN table. In the second case, instead, we need same size VLAN and routing table, and that's very easy with P4. And if you have programmable switches, because you can simply adjust the size of the tables. Clearly, you have to come with a feasible allocation of resources. But if you need the MPLS table or some other tables, you don't need to allocate memory for that. The second use case is VNF offloading. You might have seen this picture. So at ONF, we did this experiment in which we took MCord, which is our platform for mobile access. Originally, MCord, it's based on a Trellis-powered live-span fabric, couple of racks and servers. In the servers, we run VNFs. We have both control plane VNFs and data plane VNFs. What we did, we took the data plane VNF, which is the serving and packet gateway user plane, and we implemented the same functions in P4 running on the switch. So in this case, we are doing GTP tunnel termination directly on the switch. How ONOS enabled this, I'll explain to you. So we extended Fabric.P4. One of the very nice features of the recent version of the P4 language, P4 16, is that supports very well modularity. So we simply added a few more tables in the pipeline to add the serving and packet gateway capability. So we add 2 tables for the downlink and uplink processing. For the uplink, basically what you do, you simply remove the GTP tunnel. For the downlink, you want to instead add the GTP tunnel. Once we added this table, we wrote an application on top of ONOS that what it does simply implements 3GPP compliant interfaces to create, modify, delete GTP sessions. In this case, we had the serving and packet gateway control plane that was provided by Intel and Sprint. This is part of their open source EPC, talking directly to this ONOS application while thinking it was talking with the original serving and packet gateway user plane VNF. In this case, the ONOS applications is translating those requests into entries for the SP gateway tables of Fabric.P4. But it's important to know that in this case, this is a pipeline-specific application. So different from Trellis, where Trellis is a pipeline-agnostic application because it uses flow objectives. This application can work only with this P4 implementation. So to wrap up, just to recap, what's the workflow to start using ONOS with your P4 devices? Well, first you need to write a P4 program and compile it. By compiling it, you obtain a P4 info and some target-specific binaries to realize the pipeline of the device. Then you need to create a Pipeconf. To do so, you might need to write some Java code. Something I didn't mention is that those driver behaviors in Java, those are optionals, and you need to provide the Java implementation only if you want to use existing applications like Trellis, for example. If you plan to use ONOS to control your pipeline without using flow objectives or without OpenFlow-like actions or adders, you don't need to write any Java code. You can use the existing ONOS APIs to control the specific capabilities of your pipeline. Well, after you create the Pipeconf, then you can decide if you provided a pipeliner and other implementation of driver behaviors, you can decide to use existing pipeline agnostic applications like Trellis, or you can write new pipeline aware applications like serving and packet gateway control. And this is the end of my talk. And I'm happy to take any questions.
Take a couple of questions.
Yep.
There you go.
regarding management plane, so basically with P4 we have control the data plane, communication between control plane and data plane. How about management plane? Is there is a protocol called GNMI or something, something for management plane? Does P4 support anything for that? Basically some ONM operations like if there is a failure, link failure, it can be detected faster, 50 millisecond detection and correction, something like this.
The question. Well, P4 has nothing to do with that. P4 is really a language to define the pipeline, the tables. P4 runtime is a protocol to simply control those tables. And I think one of the decisions of the P4 runtime working group was that not to consider configuration at all, but leave configuration to other protocols, which is different than OpenFlow. Like in OpenFlow, you also have messages to get the port status, port counters, things like that. And things can get confusing when you have different functionalities in the same protocol, because configuration is a type of behavior that requires maybe doesn't require the shorter run rate times to program flow rules. So it's a good thing that the two things were separated. And as you said, GNMI is an example of protocol that can be used to do configuration. It doesn't have to be GNMI, it can be something else. In the case of the Stratum project, we decided to use P4 runtime along with GNMI and OpenConfig. But P4 runtime and P4 are completely independent from configuration.
Thank you.
You're welcome.
Very good talk. And I have one quick question regarding to P4. So you showed two use cases about the P4, and so one missing part would be P4 INT. So I would like to know what is the latest updates on the P4 INT support from ONOS side.
When you say INT, you mean in-band network telemetry?
Yeah, exactly.
Yeah. So we have we played around with INT. That's all I can say. I mean, we have some basic support for INT in Fabric.P4. Where in this case we provide source and transit functionality. We miss the sync functionality when it comes to hardware switches. We haven't worked on that. We have a very simple application on top of ONOS that allows you to specify the watch list rule, so for which slice of traffic you want to apply INT at the network level, and then the application, based on the topology, programs the different switches. This is similar in concept to the intent framework, but that's, I mean, it's much less than a POC, or it's good for demos. Mm-hmm. And your question is? My question is, that work can be done by G? No, in-band network telemetry is different than the telemetry, for example, exposed by GNMI. It's a process where you actually extend the packet headers to carry some state, and then at the edge of the network, you extract those headers and you send it to a collector. It's a slightly different, it's a completely different process.
Yes. In your Fabric P4 test, the data plane unit testing slide, mm-hmm. Do we need an ONOS or?
Oh, no.
Just run a script?
No, it's a Python script.
Just run a Python script and connect to your device?
Yes, correct. Correct.
So, okay, thank you.
Yeah. Last question, or?
There's one more.
Yeah.
So can you comment on how device or pipeline elasticity will be or is supported in ONOS?
Sorry, I didn't get the question.
Okay, so device elasticity would be when devices, in this case, would appear. So in other words, you're managing a new device within the scope of ONOS. The other thing is pipeline elasticity when you have a device that can support multiple pipelines, of which one of those is selected. How does it interact with, say, the higher level orchestration or management system in order to accomplish that? Or are there thoughts in that direction?
No, my thoughts. I mean, so right now the assumption is that the operator knows which pipeline is supported by a given device. So you make sure of programming the device with the pipeline you want, and that's because the compiler accepted the P4 program. If your question is, how does an orchestrator, how can you know which capabilities, which different pipelines? I'm not sure if I got your question right.
If a new device appears, how do you match up the capability? Pipeline, instance, I may want to choose among 3 different pipelines for a device.
It's the operator that manually specifies which pipeline to apply to a device.
And the APIs are present within ONOS too.
Yeah, we didn't find a use case where there could be, actually, an interesting use case could be that of Fabric in Trellis. You see a new device coming up, you understand if that device is a spine or a leaf, and then in that case, you know that that device can support both leaf.p4 and spine.p4, and then you push one or the other. But again, this is, I mean, the operator has to have knowledge of which P4 program is supported by which device. Yes, correct. Yeah.
All right. Well, thank you, Carmelo.